We are now approaching a major milestone in our learning of calculus. And that milestone is the Fundamental Theorem of calculus. And this theorem is the most important theorem that one encounters in Calc 1 and Calc 2. Its generalization is seen in Calc 3 with a whole host of theorems that manifest the basic idea in the fundamental theorem. And in fact, it gets generalized even more if one continues in their math education up to graduate level differential topology, where one works through a semester to prove what's called the generalized Stokes theorem. Okay? And these theorems are manifestations of kind of a similar concept going on, and its culmination is in the generalized Stokes theorem. But let's not think too far ahead and just consider the fundamental theorem of calculus. Okay? So we've seen before that the displacement that an object in motion has is equal to the net area of the velocity curve, the net area bounded by the velocity curve in the time axis. Okay, this x here is of course not the x of the variable along the x-axis. No, this x is the position. Okay, this x is now position, and we're using the time axis here. Okay, so if you will, this position is traditionally shown on the y-axis, whereas this t is traditionally shown on the x-axis. Okay, so we've seen before that if we want the displacement, the total displacement, this here is the delta x from A to B. Okay, so the change in position that occurs from time equals A to time equals B is the integral, the definite integral from A to B of the velocity. Well, what is the velocity? Velocity is the derivative with respect to time of the position. So take a look at this. Okay, here we have the derivative of the position function with respect to time, and the position function is of course its the antiderivative of its derivative, right? So here we don't see any primes, all right? The primes are in here. So in some sense, doing this integral sort of, in a rough way of speaking, cancels out that derivative. It's almost like it's an inverse operation of the derivative, okay? Well, here we're integrating from a fixed time A to a fixed time B. What if instead we choose to fix A, so we start our integration at some fixed A, but instead of a fixed B, we just integrate to some arbitrary time t. Okay? Now t is fixed there, it's just an arbitrary time, but it's fixed. We just don't give it exact value of it. B, you could think about it as an actual number, 3, 4. T is just a symbol representing a fixed time. And since we're using t to integrate to, we got to use a different dummy variable when we carry out that integration. So just using that relation you see here, we get that the position at time t equals t minus the position at time t equals a is equal to the integral, now integrated over this dummy variable tau, from a to t. Okay? Well, we could rewrite this and solve for x of t, the position at time t, and, well, the velocity is the derivative of position, so let's take the derivative of this. Okay, so let's take the derivative of what we just derived. So taking the derivative with respect to time, of course. Well, this is fixed, right? This is just a fixed position at time t equals a. So taking the derivative of this will just give us 0. It's just some constant there. And we end up with this expression here, okay? So notice something else. When we integrate to some arbitrary time t of the velocity curve, and then we take the derivative with respect to t, well, we get back the function that we were integrating. So in some sense, the derivative is the inverse operation of this integral. So up here, we saw how the integral was the inverse operation of the derivative, and here we're seeing how the derivative is the inverse operation of the integral. Thus, from the above reasoning, we see that there's a sort of inverse, and I write it in quotes because it's not exactly an inverse operation. Here we had to, we fixed at some, time t equals a, which we didn't give a number for. We could have chosen any number, so they're not exactly inverse in the sense that you get a unique inverse for one operation versus the other. But nevertheless, it's good in quotation marks. Okay, so you could think about them as sort of inverse operations. Okay, we're gonna need to use something called the area function here. So let f be a continuous function for t is greater than a. The area function for f with the left endpoint a. So a is part of the definition of that area function. We're starting to integrate at some t equal to a up to some arbitrary x. Okay? And here, don't confuse x with anything dealing with position. It has nothing to do with position. So this now is the x of the x-axis, if you will. Okay? So that's called the area function for f with left endpoint a. And it gives us the area, the net area, as we integrate from a to x. So nice visualization of the area function, sort of to get a mental image of the area function. Here is the area function. It's a function of x. Okay. And now definite integral, we discussed that as having the fixed lower and upper bounds. Okay. When we do the definite integral, the bounds are fixed, but x we just leave to be an arbitrary fixed point. Okay, which then will vary after we do the definite integral. So we don't specify what that x is. We do specify a. Okay, so a is totally fixed, and it is your traditional constant. X we treat as fixed as we do the definite integral, but after we do the definite integral, we actually get a function that gives us the area as x varies. Okay, and so a of x is the area that you see there in green, which begins at t equals a and ends at t equals x. So here's the fundamental theorem. Let a of x be the area function that we saw right up here and defined up here. Okay, so exactly like that. If f is continuous on a, b, then the area function itself is continuous on a and b. And not only is it continuous, it's also differentiable in the open set, open interval a to b. Moreover, the derivative of the area function gives you back this function. So the derivative of the integral from a to x of the function along the t-axis, taking the derivative with respect to x, and here be careful, okay? X is up here, it's the upper bound. So taking the derivative with respect to x, where we see this x above here, so it's the upper limit. Taking its derivative with respect to x, we get back the function. Okay, and this is what in sort of the image to have here is what we derived here. Okay, and here of course we use tau in t, while here we're using x in t. Okay, so please don't confuse or make a big deal about the dummy variables. Okay, they're just dummy variables. That's one part of the fundamental theorem of calculus. FTC stands for fundamental theorem of calculus here. Also, if f is any antiderivative of the function lowercase f, then we have that the integral of this function is equal to the difference of the antiderivative from a to b. Okay. Another way to write this is the following way. I'll use a different function. G prime of x dx is equal to g of b minus g of a. Okay, so here's the derivative in there, and on the right there is no derivative there. That's just the... And now g is an antiderivative of g prime, but we don't write it this way because why be so restrictive? This works for any antiderivative. And this also makes clear why, when we discussed the indefinite integral, which represented the family of antiderivatives, why we use the symbol but without bounds. Okay? So if f is any antiderivative, then you just take that antiderivative and evaluate f at b minus f of a, and you could get the relation you see there, the integral from a to b. And notice what we're doing here on a deeper level. We are trading a derivative in the bulk of the interval, so inside the interval. We're trading a derivative, something going on inside the interval from a to b, for a sum at the boundary of the interval. So the boundary of the interval AB is just the endpoints, okay? So we're trading a derivative in the interior of the interval for an operation at the boundary, okay? And that simple statement that I just made has very deep implications, since that generalizes all the way up to graduate level mathematics, where the general Stokes theorem is discussed. Okay, but here we'll just settle with that simple result there. Okay. So here's a sketch of the proof for the fundamental theorem. We have that the a at x plus h minus a at x, so the area function, the difference in the area function, is equal to this term there. Okay. Well, this is an integral, and we could bound it by its lower and upper limits, as we've seen in a previously discussed property. And so we then could divide by h. So we divide that whole, this whole inequality by h. So each of these, this will lose a h here, this will lose a h here, but you'll gain a h down there. And then notice something, that when h is small, so that h, x is very close to the upper limit, well, in that case, f doesn't vary very much, and so the lower limit is equal to f of x, and the upper limit will be equal to f of x as h goes to 0. And what do we have down here? Okay, what do we have in the middle there? Well, that's the difference of the area function over h, and when we take the limit as h goes to 0, that's the derivative. Okay, so a prime of x is then equal to f of x by the squeeze theorem. On the left and right, we're squeezing this into, we're squeezing the derivative of the area function between f of x. So we then have that the derivative of the area function is equal to f of x. Okay, that proves the first part. For the second part, we see from the first part that a of x is actually an antiderivative of a lowercase f. Okay, so a of x is an antiderivative, and because it's an antiderivative, any other antiderivative will differ by at most a constant. We've discussed that in a previous theorem. And so when we take this difference, we'll have this constant is just coming from expressing f as a of x plus c. And so plugging this in for fb and plugging this in for f at a, and we end up with AB. Why? Because these C's cancel. So this minus sign will distribute. And so this C would cancel with that C. But what's A at A? Well, let's take a look at our area function again. A, when we plug an A in there, is just A to A. Okay, that's 0. So this is 0. This cancels. You're left with AB. But what is AB? Well, again, take a look. Now we're plugging a B in there. And so this is what we sought to demonstrate. That's what this QED stands for, quod erat demonstrandum. That is what we sought to demonstrate in Latin. It's typical to write that in at the end of proofs. I'm not just trying to show off some Latin. Okay. And here's a visualization that may help you see why the fundamental theorem of calculus works. The black curve there is the actual function. The area function is represented by the area of the green region. And notice what happens when h gets small. H gets small. Well, then there's very little difference for f in the interval x to x plus h, right? There's a very minor change in f there that occurs. So the difference of a of x plus h minus a of x, so what you're seeing there is a of x, this is a of x plus h. And so the difference between those two is approximately equal to hf of x, and that approximation gets better and better the smaller h is. Okay, when we take the limit as h goes to 0, then we could divide this h from the right hand side and put it on the left hand side there, and so you get the difference over the difference of a over h, and that's a derivative. So that's a good motivation or visualization for why this is working. Okay, so enough theory. Let's jump into an example. So the first example is use part 1 of the fundamental theorem in order to compute these derivatives of integrals. So let's start with a, okay? And we want to compute the derivative of this integral. Notice here that we're integrating up to this variable x, okay? And we're taking the derivative with respect to x. So we'll just use the fundamental part 1 of the fundamental theorem of calculus. You could make the exact correlation by saying f of t is equal to sine squared t there. Okay. So this then would look like that's exactly what we would use in the fundamental theorem that you see above. Okay. So in that form, when we evaluate the derivative, we're going to get f of x. Okay. So what's the answer there? Sine squared of x. Okay. Not t anymore. We're done with that. I mean, that was just a dummy variable to integrate over. But when you take the derivative with respect of that bound, you then plug in that x. Notice here, that's important. this, you have x in here. Okay, so no longer t. All right. So that's our answer, sine squared x. Well, what about part B? So this time it's a little trickier because you have an x squared up there. Okay, you don't just have an x. Still, what we're going to do is define the area function in this example as starting from 0 and integrating up to x. Okay, so the traditional way to define the area function, starting with left endpoint 0. And what we seek is not the derivative of the area function with respect to x, but the derivative of the area function with x squared inside. Why is that the case? Well, look, if we have the area function that you see there, then plugging in a of, say, star, okay, would be, and what do we do when we plug in something into a function? Wherever we see that thing, so wherever we see an x, we just plug in what we put in. So we'll have a star there, okay, of cosine t squared. So this t is being squared, and it's and all of that is inside the cosine dt. So if you will, we have that there, okay? And so whatever we plug in, we end up at the top over here. So we plugged in a star, we ended up with there. If we plugged in a circle instead, well, we'll get a circle up here, okay? And we plug in x squared, what do we end up with? An x squared, okay? So we are really looking for the derivative with respect to x of a x squared, so that we get that x squared up there, okay? So how do we take the derivative of a with x squared in there? Well, we have an inside function, x squared, and we have an outside function, a. And so we're going to use the chain rule. Taking that derivative with respect to x, we take the derivative of the outside function with the inside function still plugged in, and multiply that by the derivative of the inside function. So we end up getting, for a prime, notice here, a prime of x is just the derivative of this with respect to x. Well, that's just straightforward fundamental theorem. We just get back the function evaluated at x. So we'll get cosine x squared. Okay, so if we just take the derivative of this, straightforward fundamental theorem there. And we'll need that because we need to take the derivative of the outside function. So we get that this derivative, what we're seeking, is equal to a prime x squared times 2x. That's that line. Well, the derivative of the outside function just gives you back the derivative of the area function just gives you back the original function inside, as we've seen from the fundamental theorem. So we get f, where f here is equal to cosine t squared. I should make that clear. Okay, so that's what I mean by f here, because it's what's inside the integral there of, to get the area function. And so that's the derivative of the outside function with the inside function plugged in times the derivative of the inside function. The derivative of x squared is 2x, of course. And so we get this cosine of x squared raised to the power 2 times 2x. And all of this is inside the cosine, okay? Now, where are all these, where did these two powers of 2 come from? Well, this x squared just came from this guy here, and the other x squared, the other squared there, came from that squared here, okay, in the original function, okay? Ultimately, you'll get cosine of x to the power 4 times the derivative of the inside function, which was 2x, okay? And that is how we could use the first part of the fundamental theorem in an interesting way. So the second example we'll look at is how the fundamental theorem is most commonly used. Okay, it's with part 2 there of the fundamental theorem is the typical way to use it. Okay, is the most common way to use the fundamental theorem. And so we want to use the fundamental theorem in order to compute that definite integral. And what a relief, we don't have to take Riemann sums anymore, right? All we have to do is use the fundamental theorem. So we're going to factor out that 3. We're allowed to do that. We could pull it out of the integral thanks to the constant multiple rule. And now we need to find an antiderivative of x to the 1/2. Okay, so that's how we do this. We got to find the antiderivative of x to the 1/2. What is the antiderivative of x to the 1/2? Well, one of them is x to the 3/2 over 3/2. And what this symbol is telling you is that we're going to evaluate this expression at 16 and subtract this expression at 4. Okay, so that's what you see here. We're evaluating it at 16 and subtracting it when we evaluate it at 4. And once we simplify, we get 112. And that is much easier, much quicker to get an exact result than doing Riemann sums and then having to take a limit. So the fundamental theorem is indeed our friend. Now, one might ask, well, you chose a particular antiderivative. What if you decided to choose another antiderivative? So let's choose 1 over 3/2 x to the 3/2. And this is as a side, okay? Plus 7, for example. Let's evaluate that at 4, 16. Well, then we're going to get 1 over 3/2, 16 to the 3/2 plus 7 minus 1 over 3/2 plus 1 over 3/2 times 4 to the 3/2 plus 7. And notice something here. That 7 would cancel with that 7 once you distribute the minus sign, and you just end up getting 1 over 3/2, 16 to the 3/2 minus 1 over 3/2, 4 to the 3/2. Okay? So you end up getting that same, what's inside the parentheses, that same expression inside the parentheses. We factored out the 3, so we didn't want to simplify. And now you also see why we use this symbol of the integral for the indefinite integral. And as you'll recall, the indefinite integral was a way to represent the family of antiderivatives. Okay? So in a sense, the definite integral is sort of like the indefinite integral evaluated at the endpoints, keeping in mind that you subtract the evaluation at the endpoints. Okay? So that is why we used that symbol for the antiderivative. Okay? So very important theorem, very interesting, and with very deep implications for the future.